mouth for 2 months.
Hey kids, Smath here. So, want to talk to you a little bit on this one. This is our solution video to the D&S free response questions out of chapter 3. These are gas law questions. So we're going to be trying to pull a lot of ideas about kinetic molecular theory, particles, collisions, temperature, pressure, along with a little bit of calculation. I don't think we're going to see a lot of calculation of gas laws, especially in 2020, but in the future, they may show up. So, let's go through them. This is a college prep thing. First one is classic comparison. They're giving you two gases, equal volume, equal temperature, same pressure. Everything is very, very happy. They told us we have 1 liter containers at 25 degrees Celsius, 1 atmosphere of pressure. And these are going to be, very factual type of questions, very explanatory type of questions. So the first one says, decide whether each statement is true or false and explain your reasoning. So the number of moles of SO3 is larger than the number of moles of NO. And remember, we need to explain our answer to these. So what my explanation would be is to A, I would say, first off, this is a false statement. Why is this a false statement? Because Avogadro's hypothesis, not just Avogadro's number, but Avogadro's hypothesis, which states that at the same conditions, what are those conditions, you ask? I'm glad you asked. The same conditions of temperature, pressure, and volume. Look, they're right there. Temperature, pressure, and volume. Under the same conditions of temperature, pressure, and volume, we will have the same number of moles, the same number of particles. So if they're under the same conditions, the number of moles of SO3 is not going to be larger. How about B? The average speed of SO3 is lower than the average speed of N2. Now be careful with this one because I have a tendency every now and then I'll get speed and kinetic energy mixed up. That could be pretty deadly. This is actually very true. How come? Because my explanation would be same conditions. They're going to have the same kinetic energy. And if they have a different mass, then the higher molar mass would have a lower, now let's be consistent here, Steve. I would have a lower velocity. That's absolutely true. Then they follow that up with the one that we want to hear, and that is, hey, what about the average kinetic energy of SO3? Oh, well, that's a different story. That's absolutely false. The average SO3 molecules are greater than the kinetic energy of the N2. That's a false answer because we all have already said temperature is directly proportional to kinetic energy. Same temp, same kinetic energy. Fantastic. D says, hey, what about the mass of SO3 in the second container will be the same as the mass of the N2 in the first container? And we all know that's absolutely false. So how do we explain that? We simply say the moles are equal but molar mass is 28 for N2, 28 grams per mole for N2, which is not equal to 80 grams per mole of SO3. Easy questions. Give them a good explanation that goes along with it, though. So that's problem one down. Comparison of two containers. This is a very common problem on the AP historically. Sometimes it's two containers side by side. Sometimes it's 2 or 3 or 4 balloons that are side by side, and they say, what's the same, what's different? Kinetic energy is the same, velocity is different, mass is different, molecules or moles are the same. Okay? Let's look at question 2. Now we get into a little bit of calculation with things. They give us 800 millimeters of mercury. That's going to convert on over. Divide that 760 millimeters mercury. That's going to give me 1.05 grams, or excuse me, atmospheres. Looked at a different problem. They want to know how many moles. No problem. That's a 1.05 atmospheres in 560 liters equals N. R is going to be in atmospheres, 0.02 liter atmospheres per mole Kelvin. This is a real easy gas law calc. And my temperature now is 273 Kelvin. Solve out N. N is going to be 0.0263. And then the second part of that problem B says, what's the molar mass? No problem. We take 1.55 grams over 0.0263 moles, and we get a molar mass of 58.9 grams per mole. They're not asking for an identification. If they, you know, what element is it? Okay, we could say it's probably closest to iron, would be our best bet, but a real easy molar mass calc. C has a little bit of pro and con. I like parts of this. One of the best parts I like is A, write a balanced chemical equation for this. They tell us that NH4NO3 breaks apart into H2O plus N2 plus O2. And you're saying, how did you know to put that 2 out in front of that NH4NO3? Well, they told me that it broke into nitrogen. So since I knew that the nitrogen was going to be diatomic on this side and it didn't have a diatomic here, I might as well throw a 2 out there. Now, what's that going to do to my hydrogen? It's going to make my hydrogen 8, which means I'm going to need to have a 4 in front of that. And my oxygen ends up working out as 2 times 3, which is 6. I get 4 from the water and 2 from the diatomic oxygen. So that's a balanced chemical reaction for us here. That works out pretty smooth. Then it says, imagine, what if all the products were gaseous and you started out with 4 grams? No problem, 4 grams of NH4NO3. Molar mass of that is 80 grams per mole. Whoops. Sorry. 80 grams per mole of NH4NO3. And then use your coefficients. 2 moles NH4NO3. And my coefficients, all the products are gaseous, which means I need to add together 4, 5, 6. Wait a minute. Oh gosh, I need a 2 out in front of that. You guys probably are already saying, Smath, forgot a 2 there. 4, 5, 6, 7 moles of products. I caught it. So that's going to be a total number of gaseous products, 175 moles. That's my answer to B. In C, what's the total number of molecules? You ain't getting this question this year. Way too easy. It's pretty easy any year. 0.175 moles. Turn those into molecules. 1 mole, 602, 10 to the 23rd. Molecules. And that's just going to give me a 1.05, 10 to the 23rd molecules. I apologize. My handwriting's really bad today. I need to slow down and make this better. Now it says, hey, what if, go back to your gas laws. Remember, there's a gas law chapter. What's the total volume going to be? Well, we know the total number of moles. Now they changed the conditions on us, or they gave us conditions, 527, 745. So I'm going to trust you guys are going to convert that 745 to 0.98 atmospheres. And you would show that, but my P would be 0.98 atmospheres. V, they gave us as V is what we're looking for. V equals N, which is the 0.175 moles. R, 0.082 liter atmospheres per mole Kelvin, and my temperature was 527 kelvins. V for this ends up being 7.56 liters. So there you go, 3 gas law problems. All of them a little bit different. First one, comparison, kinetic theory. Second one, third one, a little bit more calculation based, using some stoichiometry and using some other principles. This is a good gas law review for us, FRQs. Hopefully some of it shows up on this year's AP. I'm Smath. I hope this video helped.